Imagine looking back in time to the very first light in the universe, not just a faint glow, but a relic holding secrets to the cosmos' birth. This ancient light, the cosmic microwave background, isn't what you think it is, and its true story is more mind-bending than any sci-fi movie. Get ready to uncover the universe's greatest mystery. When we talk about the universe's oldest light, we are really stepping back into a time so distant and so unlike anything we can imagine that our very language struggles to capture it. It is a journey back nearly 14 billion years to the very moment when the cosmos itself was still a newborn, restless and chaotic, bursting with energy and possibility. This ancient light, which we now call the cosmic microwave background, was born about 380,000 years after the Big Bang. That may sound like a large number, but compared to the universe's current age, it is astonishingly short, a mere heartbeat in cosmic terms. If we imagine the entire history of the universe compressed into a single year, with the Big Bang occurring at midnight on January 1st, this light would appear in the first few minutes of that cosmic calendar. In those first 380,000 years, the universe was nothing like it is today. It was a dense hot soup of particles, protons, electrons, photons, and neutrinos, all colliding and interacting at such high energies that atoms could not form. Light itself could not travel freely because photons, the particles of light, were constantly bouncing off free electrons in a process called scattering. Imagine trying to see across a room filled with dense smoke. No matter how strong a flashlight you shine, the light cannot pass through without being scattered in every direction. That was the early universe, opaque, radiant, and turbulent. During this era, which cosmologists call the photon baryon plasma stage, photons and matter were tightly coupled, locked together in a kind of cosmic dance. Gravity tried to pull matter into clumps while radiation pushed back outward, creating ripples, waves of compression and rarefaction, similar to the vibrations of sound waves traveling through air. In fact, you could say that the early universe was singing, its energy oscillating in patterns that would one day shape the structure of galaxies and clusters. But at that point it was all hidden behind a veil because no light could escape to carry information. Then came the great transition. As the universe expanded, it cooled. Temperatures dropped from billions of degrees to thousands, eventually reaching a critical point, about 3,000 Kelvin, where protons and electrons could finally combine to form neutral hydrogen atoms. This moment is called recombination. It was a turning point of staggering importance because once atoms formed, the electrons were no longer freely available to scatter photons. Suddenly, light was freed. Photons decoupled from matter and began to stream across the universe, no longer trapped in the dense plasma. This was the birth of the universe's oldest light, the cosmic microwave background. In that instant, the universe transformed from opaque to transparent, much like a fog lifting on a bright morning. For the first time, light could travel unimpeded, carrying with it a snapshot of the conditions that existed at that moment. That ancient glow, stretched and cooled by billions of years of cosmic expansion, still surrounds us today, though it has shifted into the microwave region of the spectrum, invisible to human eyes. Sensitive instruments can capture it as a faint, uniform radiation filling the entire sky. This event, when light first escaped, was not only the beginning of the cosmic microwave background but also the earliest photograph of the universe. When astronomers study this light, they are essentially looking at the universe's baby picture frozen in time. That image reveals a universe that was remarkably smooth but not perfectly uniform. There were tiny fluctuations in temperature, just 1 part in 100,000, but those minuscule variations contained within them the seeds of everything we see today. Without those imperfections, gravity would not have had the foothold it needed to pull matter into clumps, and galaxies, stars, and planets, including our Earth, would never have formed. But the significance of this moment goes deeper still. Think of what it means that photons released nearly 14 billion years ago are still traveling, still reaching us across the vast expanse of space-time. Every time we detect the faint glow of the cosmic microwave background, we are intercepting messages from the dawn of creation. Those photons have traveled longer than the lifespan of any star, longer than the age of any galaxy, crossing distances so immense that they stretch our comprehension. And yet they remain coherent, detectable, and rich with information about the universe's infancy. The discovery of this ancient light was itself a story of serendipity and persistence. In 1965, two scientists at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate static from their radio antenna. No matter what they did, cleaning the equipment, recalibrating, even shooing away pigeons nesting in the antenna, they could not get rid of the faint background noise. Eventually, they realized that the static was not interference at all, but the very echo of the Big Bang, the cosmic microwave background. That accidental discovery earned them the Nobel Prize and opened an entirely new era of cosmology. What had once been an abstract idea, that the universe had a hot, dense origin, was suddenly confirmed by direct evidence. The universe's oldest light had revealed itself to us, whispering across eons. Since then, increasingly precise instruments, like the COBE satellite in the 1990s, followed by WMAP in the 2000s, and the Planck Observatory more recently, have mapped this radiation in exquisite detail. These maps are not just beautiful images, they are scientific gold mines showing us the patterns of those primordial fluctuations with incredible accuracy. Every tiny hot and cold spot in the cosmic microwave background corresponds to a slight over or underdensity in the early universe, which later grew into the cosmic web of galaxies we observe today. To truly appreciate this, imagine looking at an ultrasound of a developing child. The fuzzy outlines on the screen may not look like much, but to those who understand them, they hold the blueprint of the future. In the same way, the cosmic microwave background may appear as nothing more than a mottled pattern of temperature differences, but within those patterns lies the story of how the universe would evolve. It tells us not just where we came from, but also the physics that governed the earliest moments of existence. And yet, what is perhaps most remarkable is the humility this discovery imposes on us. To realize that the light we measure today began its journey billions of years before the Earth even existed, before the Sun was born, before galaxies had coalesced, is to confront the sheer scale of cosmic time. Our lives, our histories, even the lifespan of civilizations, are fleeting compared to the voyage of those photons. They began their journey when the universe was a fireball, and they arrive at our telescopes after witnessing everything that has happened since. But this light is not only a relic, it is a key. It encodes within its faint variations the laws of physics that shaped everything. By studying it, scientists have been able to determine the age of the universe, its rate of expansion, its composition, and even its geometry. The fact that we live in a universe that is flat on cosmic scales rather than curved was revealed through this very light. The fact that dark matter dominates ordinary matter in shaping cosmic structure, and that dark energy drives the acceleration of expansion, also comes from decoding its patterns. Without the birth of this light, we would be blind to the grand architecture of the cosmos. What is even more humbling is that this light exists everywhere. No matter where you look in the sky, you see it. It is not confined to one direction or one region. It permeates the entire universe, like the echo of a great cosmic symphony. That universality tells us something profound, that the universe at its birth was incredibly uniform, governed by the same laws and filled with the same energy everywhere. The very fact that the cosmic microwave background is so even across the sky confirms that the universe emerged from a common origin. So when we speak of the birth of the universe's oldest light, we are not just recounting a scientific milestone. We are telling the story of how the cosmos first revealed itself to itself. Light is information, and without it we would have no way of knowing what lay beyond our immediate horizon. The moment photons were freed, the universe became a place that could one day be observed, studied, and understood. In a very real sense, the act of light escaping was the act of the universe becoming knowable. For us as human beings, this story carries more than scientific value, it carries symbolic weight. That moment of liberation when photons broke free and began their eternal journey is a metaphor for illumination itself. It is the idea that clarity emerges after struggle, that understanding follows after obscurity. The universe was once a fog, impenetrable and opaque, and then it cleared and light was born. In our own lives, too, there are moments when the fog lifts, when insight pierces confusion, when what was hidden becomes visible. In that sense, the universe's oldest light is not only a scientific phenomenon, but also a lesson in patience and discovery. To stand under the night sky today, knowing that every patch of darkness is bathed in this ancient glow, is to feel both small and infinite, small because we are but a flicker compared to the vastness of time and space. Infinite because we are capable of perceiving it, of asking questions, of uncovering truths that lie hidden in radiation nearly as old as time itself. The birth of the universe's oldest light is not just a tale of photons and atoms. It is a testament to curiosity, to persistence, and to the enduring human desire to understand where we come from. And so, when we speak of the universe's oldest light, let us not think of it only as radiation detected by machines, but as a bridge that connects the fiery birth of the cosmos to the present moment. A bridge that ties together the infancy of everything with the consciousness of beings who now gaze at the stars and ask why. That bridge began when the fog lifted, when the plasma cleared, when photons were freed. And across that bridge, the universe has been speaking to us ever since in a language written in light. When we speak of the universe's oldest light as a cosmic time capsule, we are touching on one of the most extraordinary truths in all of science. That light is not only energy but memory. Every photon that reaches us carries a record of where it has been, of the conditions under which it was born, and of the journey it has taken across the immeasurable vastness of space. The cosmic microwave background, the afterglow of the Big Bang, is the most profound example of this truth. It is not merely radiation, it is a messenger from the dawn of time, carrying within it the history of the universe's earliest moments. It is as though the cosmos itself placed its story inside a sealed container and sent it forward through billions of years, waiting for beings with the curiosity and intelligence to finally open it and understand. To understand why the cosmic microwave background is called a time capsule, we must first think about what it means to look at the night sky. Every star we see is not shining as it is today, but as it was in the past. The light from our closest star, the Sun, takes about 8 minutes to reach Earth, which means we are always seeing the Sun 8 minutes in the past. The light from the nearest star system beyond the Sun, Alpha Centauri, takes more than 4 years to arrive, which means we see that star system as it was 4 years ago. The farther we look into space, the further back in time we are gazing. When astronomers peer at galaxies millions of light years away, they are seeing those galaxies as they were millions of years in the past. This simple truth, that distance in space is also distance in time, transforms our telescopes into time machines. Now imagine extending this principle as far as possible. If we keep looking deeper, beyond nearby stars, beyond distant galaxies, beyond even the clusters and superclusters of galaxies, we eventually reach a wall, the limit of what can be seen. That wall is the surface of last scattering, the moment when the universe's first light was released about 380,000 years after the Big Bang. Beyond that moment, the universe was opaque and photons could not travel freely. So the farthest back we can see in light is to that ancient boundary, and what do we find there? The faint glow of the cosmic microwave background, bathing the entire universe in a nearly uniform radiation. It is not just a background glow, it is the earliest visible light in existence, the ultimate time capsule, showing us the conditions of the universe at that precise moment in its infancy. The incredible thing about this time capsule is its endurance. Imagine burying an artifact in the ground, hoping that thousands of years later someone might discover it. Over time, weather, erosion, and accidents might destroy it or alter it beyond recognition. But this cosmic time capsule has survived for nearly 14 billion years, untouched and unbroken. The photons that make up the cosmic microwave background have been traveling through space since their release, mostly uninterrupted, carrying their information faithfully across unimaginable distances. They have crossed through the formation of galaxies, past exploding stars, through regions of space warped by gravity, yet still they arrive, whispering the conditions of the young universe into our instruments. It is remarkable to realize that this light has been present all along. Long before telescopes existed, long before human beings even walked the Earth, the cosmic microwave background was already streaming through the cosmos, invisible but ever present. It has been raining down on Earth for billions of years, but we only discovered it in the 20th century when our technology became sensitive enough to detect it. Before that, the universe's greatest time capsule had been open around us, and yet we did not know how to read it. That discovery was like suddenly realizing that you had been living inside a library all your life without knowing how to open the books. Once the door was unlocked, a flood of knowledge poured out. When scientists first measured the cosmic microwave background, they were struck by its uniformity. It seemed to confirm that the early universe was hot, dense, and nearly the same everywhere. But as instruments improved, tiny variations emerged, fluctuations in temperature and density only a few millionths of a degree apart. These seemingly minor differences were monumental in significance. They were the fingerprints of the universe's formation, preserved in the time capsule for billions of years. They showed us where matter was slightly denser, where gravity would later draw material together to form galaxies and stars, and where matter was slightly thinner, leaving behind the great voids of space. Without these fluctuations, the universe would have remained a smooth, featureless expanse, never forming the cosmic structures we see today. In the faint patterns of this ancient glow, the future of the universe was already written. Think of it this way: the cosmic microwave background is like an ancient parchment filled with writing, though most of the words are faded or obscured. With each new advance in technology, scientists learn to read more of the script, uncovering details that had been hidden for billions of years. The COBE satellite gave us the first hints. WMAP revealed the delicate patterns more clearly, and the Planck Observatory provided the most detailed map yet, showing the early universe with astonishing precision. Each mission deepened our understanding of what the time capsule contained, like archaeologists uncovering layer after layer of an ancient buried treasure. The information contained in this light has transformed cosmology from speculation to science. From it, we have learned the exact age of the universe, 8 billion years. We have learned its composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy. We have learned its geometry, flat on the largest scales, not curved. We have even been able to test fundamental physics, because the patterns in the microwave background reveal the conditions under which the laws of nature operated in the earliest moments. Without this time capsule, our understanding of the cosmos would be like trying to piece together a puzzle with most of the pieces missing. With it, we have a clear window into the first chapter of everything. The poetic beauty of the cosmic microwave background is that it carries both the simplicity of the past and the complexity of the future. On one level, it shows a universe that was nearly uniform, filled with light and energy, smooth and calm. On another level, hidden in that simplicity were the tiny seeds of all the complexity that would follow, the galaxies, stars, planets, and eventually life itself. The time capsule reminds us that great things emerge from small beginnings, that the tiniest variations can blossom into structures of unimaginable grandeur. It is a lesson written not just in science, but in existence itself. And yet, there is something deeply humbling about the idea that this time capsule was not prepared for us. The universe did not design the cosmic microwave background as a gift for humanity. It is simply the natural byproduct of cosmic evolution, a relic of physical processes unfolding on scales far beyond our influence. And yet, here we are, a species on a small planet orbiting a modest star, capable of detecting and interpreting this ancient signal. The fact that we can do so is a testament to the power of human curiosity and ingenuity. It is as though we stumbled upon a message written not to us, but for anyone who could one day learn to read the language of the cosmos. What makes this even more profound is that the time capsule is universal. No matter where you are in the universe, if you had the right instruments, you would see the same background radiation. A civilization on the other side of the cosmos, orbiting a distant star in a far-off galaxy, would detect the same ancient glow. The time capsule is not Earth's possession, it is the universe's common heritage, available to any who can unlock it. In that sense, it unites all intelligent life, wherever it may arise, in a shared connection to the same cosmic origins. This universality is also why the cosmic microwave background is so important to science. Because it is everywhere, it serves as a fixed reference point, a backdrop against which we can measure everything else. Astronomers use it to calibrate distances, to study the distribution of matter, and to test theories of gravity and physics. It is the foundation upon which modern cosmology rests, the bedrock of our understanding of the universe. Without it, our cosmic story would be far less certain, but the time capsule is not infinite. The further back we try to look, the closer we get to the Big Bang itself, and beyond that lies a region we may never see. Before the release of light at recombination, the universe was opaque, and photons could not escape. To peer beyond that wall, scientists must use other messengers, neutrinos, gravitational waves, or perhaps new particles yet to be discovered. The cosmic microwave background is the earliest light we will ever see, but not necessarily the earliest signal we can detect. It is the gateway to deeper mysteries, pointing us toward questions that remain unanswered. Still, what we already have is extraordinary. Every photon in the microwave background is a survivor, a traveler from the edge of time. To detect them is to hold in our instruments the most ancient relics in existence. It is to open a capsule sealed not by human hands but by the unfolding of the cosmos itself. And when we open it, we find not gold or jewels, but something far more precious, knowledge. Knowledge of how everything began, of how it grew, of where it is headed. In a way, the cosmic microwave background is like the memory of the universe. Just as our personal memories shape who we are, this cosmic memory shapes the story of everything. Without memory, a person has no continuity, no sense of self. Without the cosmic microwave background, the universe would be without its first recorded history, and we would have no way to connect our present to its distant past. By studying it, we are not only learning about the cosmos, we are connecting ourselves to its deepest identity. And so, when we call the universe's oldest light a time capsule, we do not exaggerate. It is a vessel of memory, a preserved echo of the moment when light first broke free. It has traveled across billions of years and billions of light years, unchanged and enduring, waiting for someone to finally open it. That we have done so is one of humanity's greatest achievements, a triumph not of conquest or power, but of curiosity and wonder. It is proof that in the vast darkness of space, light persists, memory endures, and truth can be found if we are willing to look deeply enough. When scientists first looked at the universe's oldest light in detail, they were astonished by what they saw. At first glance, the cosmic microwave background appeared almost perfectly uniform, a smooth glow stretching across the entire sky. This was in itself a remarkable confirmation of the Big Bang, proof that the universe began in a hot, dense state and has been expanding ever since. But as instruments grew more precise, something extraordinary emerged from beneath that smooth surface. Tiny fluctuations in temperature, minuscule variations in density, ripples hidden in the afterglow of creation. These ripples were not random noise, nor were they imperfections in the measurements. They were the imprints of something fundamental, the earliest seeds of cosmic structure, the first hints of the universe shaping itself into galaxies, stars, and planets. These ripples were astonishingly small, just 1 part in 100,000. To our eyes, they might seem insignificant, almost meaningless in their subtlety, but in the grand scale of the cosmos, these tiny variations meant everything. They were the blueprint of the universe's future, the first sketch of the grand cosmic architecture. Without them, the universe would have remained a featureless sea of matter and energy. Gravity would have had nothing to work with, and no stars or galaxies would have ever formed. These faint imprints were, in truth, the fingerprints of creation itself. To understand how these ripples arose, we must return to the universe's infancy, to the moments before the cosmic microwave background was born. In the first few 100,000 years, the universe was a plasma of protons, electrons, and photons, so dense and hot that light could not escape. In this fiery environment, matter and radiation were locked together in a delicate balance. Gravity tried to pull matter into clumps, but radiation pushed back, creating oscillations, waves of compression and rarefaction, that rippled through the plasma. These oscillations were like sound waves traveling through the young universe, vibrations imprinted on the very fabric of reality. When the universe cooled and atoms formed, freeing light to travel across space, those oscillations were frozen into place. The photons that escaped carried with them a record of the ripples, a permanent signature of the sound of the early cosmos. It is these frozen ripples that we now observe in the cosmic microwave background, appearing as faint hot and cold spots across the sky. Each fluctuation tells us where matter was slightly denser or slightly thinner, where gravity would later draw together the first galaxies, and where emptiness would grow into the great cosmic voids. The discovery of these ripples was a triumph of human ingenuity. When Arno Penzias and Robert Wilson first stumbled upon the cosmic microwave background in 1965, they detected only its uniform glow. It was not until the launch of the Cosmic Background Explorer (COBE) in 1989 that scientists first saw evidence of these subtle fluctuations. The data showed that the universe's oldest light was not perfectly smooth, but instead dappled with tiny variations. It was like staring at a blank canvas and suddenly realizing that, beneath the surface, there was a hidden painting of unimaginable complexity. Later missions, such as WMAP and the Planck satellite, revealed the picture in even greater detail, mapping the ripples with breathtaking precision. The importance of these ripples cannot be overstated. They are the reason we are here today. Imagine for a moment that the early universe had been perfectly smooth, with no variations at all. Gravity would have had nothing to act upon. Matter would have been evenly distributed, never collapsing into stars, galaxies, or planets. The universe would be a cold, dark void, devoid of structure, devoid of life. The fact that there were tiny imperfections, tiny ripples, in the early cosmos is the reason why the night sky is filled with galaxies, why stars burn, and why life on Earth exists. The beauty of our existence is, in a sense, built upon the imperfections of creation. These ripples also tell us something even more profound. They are evidence of events that happened in the very first fraction of a second after the Big Bang. According to the theory of cosmic inflation, the universe underwent a rapid expansion in its earliest instant, growing from subatomic scales to cosmic size in a fraction of a heartbeat. This expansion stretched quantum fluctuations, minute uncertainties in the distribution of energy, into the macroscopic ripples that we now see frozen in the cosmic microwave background. In other words, the hidden ripples in the universe's oldest light are the magnified fingerprints of quantum processes, the bridge between the smallest scales of physics and the largest scales of the cosmos. It is as though the universe took the tiniest whispers of the quantum world and amplified them into the grand symphony of galaxies we see today. The patterns of these ripples are not random. They contain harmonies and rhythms, like the echoes of a great cosmic orchestra. Scientists study them using a tool called the power spectrum, which shows how fluctuations of different sizes contribute to the overall picture. This spectrum reveals a series of peaks and troughs, corresponding to the oscillations of matter and radiation in the early universe. By analyzing these patterns, cosmologists can extract an astonishing wealth of information: the density of matter, the amount of dark matter, the strength of dark energy, even the shape of the universe itself. All of this knowledge is hidden in the faint ripples imprinted in light nearly 14 billion years old. Think about the poetry of this for a moment. The universe's largest structures, galaxies, clusters, the great cosmic web that stretches across billions of light years, were seeded by fluctuations so tiny they were born in the quantum foam of the infant cosmos. Every galaxy that sparkles in the night sky owes its existence to a minute variation in the density of the early universe. Every star that has ever shone, every planet that has ever orbited, every being that has ever lived, all trace their origin back to these faint ripples frozen in ancient light. The grandest scales of existence are linked to the smallest. The vast and the minute are bound together in a cosmic dance, with the ripples serving as the bridge between them. The story of the hidden ripples of creation is also a story of patience and precision. For decades, Scientists built instruments capable of measuring differences in temperature of just millionths of a degree. They launched satellites into space to escape the interference of Earth's atmosphere. They developed sophisticated algorithms to separate the signal of the cosmic microwave background from the noise of nearby galaxies and dust. And with each improvement, the hidden picture became clearer, until today we can see the ripples in stunning detail. The image produced by the Planck satellite, with its mottled blue and red spots, is one of the most important maps ever created. It is a map not of the Earth nor of the stars, but of the universe itself at the dawn of time. What these ripples teach us extends beyond science into philosophy and even spirituality. They remind us that perfection is not the foundation of creation, imperfection is. It is the tiny irregularities, the subtle variations that allow for growth, change, and beauty. Without ripples, there would be no galaxies; without galaxies, no stars; without stars, no planets; and without planets, no life. In the same way, in our own lives, it is often the challenges, the variations, the imperfections that shape us, that give rise to meaning and richness. The universe's hidden ripples are not just a scientific fact. They are a lesson written into the very fabric of existence. The ripples also confront us with a profound sense of connectedness. When we look at the cosmic microwave background, we are not seeing something distant and unrelated to us. We are seeing our own origins, the atoms in our bodies, the air we breathe, the ground beneath our feet. All of it traces back to the structures formed from those primordial fluctuations. In a very real sense, we are made of ripples, born from the tiny imperfections imprinted in the universe's first light. To study them is to study ourselves, to glimpse the roots of our existence. And perhaps the most astonishing truth of all is that these ripples are still speaking to us. Though they were frozen billions of years ago, their message endures. They tell us not only about the past, but also about the future. They reveal that the universe is expanding faster and faster, driven by dark energy. They show us that dark matter, though invisible, shaped the cosmic web. They even hint at physics beyond what we know, offering clues to mysteries we have not yet solved. The ripples are not static, they are alive with information, a conversation across time between the universe's birth and its unfolding destiny. To stand under the night sky, knowing that behind every star and galaxy lies the echo of these ancient ripples, is to feel awe. It is to recognize that we live in a universe that carries its history within itself, that remembers its own birth in patterns of light. It is to realize that we, too, are part of that story, small ripples ourselves in the ocean of existence. So when we speak of the hidden ripples of creation, let us remember that they are not just marks on a scientific map. They are the origin of structure, the foundation of galaxies, the seeds of stars, and the roots of life. They are the bridge between quantum uncertainty and cosmic grandeur. They are the imperfections that gave rise to beauty. They are the whispers of creation, still echoing across time, waiting for us to listen. And when we listen, when we truly hear what they are saying, we discover not only the story of the universe, but the story of ourselves, written in the faintest ripples of light. When scientists first began studying the faint radiation that we now call the cosmic microwave background, they expected it to be a simple leftover, a uniform glow spread evenly across the sky. In the earliest analyses that seemed to be true, an almost perfect blackbody radiation signature, consistent with the idea that the early universe was once unimaginably hot and dense. But as instruments grew more sensitive and measurements more precise, surprises began to emerge. What we thought would be a straightforward confirmation of the Big Bang turned into a treasure chest of unexpected revelations about the universe's true nature. Instead of just a snapshot of the cosmos' childhood, the oldest light became a coded message containing secrets about the hidden forces that govern existence. Among these, the most astonishing discoveries were the confirmations of dark matter and dark energy, two invisible phenomena that today dominate cosmology. The first major revelation was that the ordinary matter we see, the stars, planets, dust clouds, gas, and everything built from atoms, makes up only a small fraction of the universe's total contents. When scientists mapped the subtle fluctuations in the cosmic microwave background, they noticed something peculiar. The way these ripples were distributed, their relative sizes, and the patterns they created didn't align with a universe made purely of normal matter. There was more gravitational pull than visible matter could account for, and the only explanation was that some unseen mass was present, tugging on the fabric of space-time and influencing how structures formed. This was not an entirely new suspicion. Astronomers like Fritz Zwicky in the 1930s and Vera Rubin in the 1970s had already seen hints of this in galaxy motions, but it was the CMB that sealed the case with undeniable clarity. The universe's oldest light showed us that without this invisible mass, what we now call dark matter, the galaxies, stars, and planets we see today could never have formed. This revelation alone was shocking because it suggested that the cosmos is filled with something that does not emit, absorb, or reflect light. It doesn't behave like ordinary matter, it doesn't form atoms, and it seems to pass through normal matter almost as if it isn't there at all. And yet, without it, the story of creation as we know it would be impossible. The tiny ripples imprinted on the cosmic microwave background became the gravitational seeds for large-scale cosmic structures, and dark matter's presence ensured those seeds could grow into galaxies. Without dark matter, the early universe's matter would have been too evenly spread out, and gravity would never have been strong enough to pull it together. In other words, the universe's oldest light revealed not only that dark matter exists, but also that it has been the silent architect of cosmic structure since the very beginning. As if that were not enough, another revelation emerged from this same light. The universe is not only expanding, but doing so in a way that defied earlier predictions. Scientists had long known about cosmic expansion thanks to Edwin Hubble's discovery in the 1920s. But the question of whether expansion was slowing down or speeding up remained unanswered for decades. The expectation was that gravity would gradually slow expansion, perhaps even reversing it in a big crunch. However, when cosmologists analyzed the data imprinted in the CMB and combined it with later observations of distant supernova, a startling truth came to light: the universe's expansion is accelerating. Instead of slowing, galaxies are rushing away from each other faster and faster, as though some mysterious force is pushing the fabric of the universe apart. This force was given the name dark energy, and it now accounts for nearly 70% of the cosmos. To grasp how revolutionary this discovery was, imagine living in a world where gravity is the only force you believe controls cosmic destiny, only to realize that there exists another, much stronger influence, invisible and poorly understood, shaping everything. Dark energy does not behave like matter or radiation. It appears to be woven into the very structure of spacetime itself, exerting a kind of repulsive effect that overwhelms gravity on large scales, and the CMB, that oldest of lights, was essential in pointing us toward this truth. By measuring the geometry of the universe through the fluctuations in the CMB, scientists realized the cosmos was flat, not curved, which meant something unknown had to be balancing the total energy density. That something was dark energy. To call these findings surprising would be an understatement. The discovery of dark matter and dark energy upended our view of the universe. Before the CMB revelations, we believed we lived in a cosmos largely governed by the familiar, the atoms and forces we experience in our daily lives. Afterward, we were forced to accept that the known, visible universe is only the tip of the iceberg. Ordinary matter accounts for less than 5% of the total content of the cosmos, while the rest is made up of dark matter and dark energy. That means that everything we see, the galaxies shining in the night sky, the earth beneath our feet, the cells in our bodies, is an almost insignificant fraction of reality. We are, in effect, living in a universe ruled by forces that are invisible, mysterious, and barely understood. What makes this revelation so profound is not only what it tells us about the present, but also what it implies about the past and future. Dark matter, revealed through the imprints on the oldest light, acted as the framework around which galaxies could grow. Without it, the luminous beauty of the cosmos would never have emerged. Dark energy, on the other hand, is dictating the universe's destiny. If its influence continues as it has, the cosmos will keep expanding forever, galaxies drifting farther and farther apart until the night sky grows dark and lonely. Alternatively, if its strength changes over time, the fate of the universe could take other strange turns. All of these scenarios were hidden within the faint whispers of ancient photons until we learned how to listen. The unexpected revelations of the CMB also forced us to confront the limits of human understanding. Here was a light that had traveled nearly 14 billion years, carrying secrets that no human could have guessed unaided. The instruments we built, satellites like COBE, WMAP, and Planck, became our translators, decoding this faint signal with exquisite precision. What they told us was both humbling and exhilarating. We learned that the universe is far stranger and more magnificent than our imagination had dared. In the ripples of ancient radiation, we discovered not only confirmation of the Big Bang, but also evidence for an entirely new cosmic paradigm, one where the majority of reality is hidden in the dark. This shift in perspective has not only changed science, but also philosophy. To know that most of existence is invisible challenges our sense of certainty. It reminds us that human perception is narrow, that what we see with our eyes is only a small sliver of what truly exists. The oldest light taught us humility, showing that we are not at the center of understanding, but merely at the beginning of a much larger quest. Every answer it gave raised new questions. What is dark matter made of? Is it composed of undiscovered particles? Could it interact with itself in ways we have yet to see? And dark energy, what is its true nature? Is it a property of space itself, or the sign of new physics beyond our current theories? These questions burn brightly in the minds of cosmologists, fueled by the revelations hidden in that ancient glow. The cosmic microwave background also revealed another surprising truth. The universe is remarkably uniform and yet finely tuned with just enough irregularity to create complexity. Those fluctuations in temperature and density were tiny, on the order of 1 part in 100,000, but they were enough to seed the vast structures we see today. That balance between smoothness and roughness seems almost miraculous. Too smooth, and no galaxies would form. Too rough, and the universe would collapse into chaos. The fact that the oldest light revealed such a delicate balance is itself a revelation about the extraordinary conditions that gave rise to everything we know. When we reflect on these revelations, it becomes clear that the universe's oldest light is not simply a relic. It is a living teacher, a cosmic archive that continues to guide us. Each new generation of instruments sharpens the picture, uncovering new details, refining our measurements of the universe's age, composition, and expansion rate. And with every step, the unexpected continues to emerge. What began as a study of a faint background glow has blossomed into an exploration of the deepest mysteries of existence. To look at the CMB is to look back in time, but also to look forward, because the discoveries it reveals reshape the trajectory of human inquiry. Dark matter and dark energy are not the end of the story, they are the beginning of a new chapter. The oldest light tells us that reality is more expansive than we once thought, and that the true origins of the universe are even more mysterious than the Big Bang alone. It shows us that our task as seekers of knowledge is not just to confirm what we already believe, but to open ourselves to the possibility of surprise. In the end, the cosmic microwave background gave us more than scientific data. It gave us wonder. It reminded us that the universe in its vastness is not indifferent but full of secrets waiting to be uncovered. The greatest revelations are not always the ones we expect, and the most profound truths are often hidden in the faintest whispers. The universe's oldest light whispered to us about dark matter and dark energy, and in listening, we discovered that the cosmos is stranger, deeper, and more magnificent than we could have ever imagined. When we look at the universe's oldest light, the cosmic microwave background, it feels as though we are gazing into a time long before the world as we know it existed. It is tempting to think of this light as a window to the past, a way of studying what the cosmos was like in its infancy. But the more carefully scientists have examined it, the clearer it has become that this light does not simply tell us where we came from. It also gives us clues about where we are headed. Hidden in the subtle ripples, the faint variations in temperature and density, is a kind of cosmic blueprint, a record not only of the birth of structure, but also of the universe's destiny. It is an astonishing truth. The oldest light is not merely a story of beginnings, it is also a map of the future. The most immediate way the cosmic microwave background reveals the future is through its description of the universe's composition. By carefully analyzing the proportions of ordinary matter, and dark energy imprinted in that ancient glow, scientists can model how the cosmos will evolve. If you know how much of the universe is made of each ingredient, you can predict how structures will continue to grow, how galaxies will cluster, and how expansion will unfold. In essence, the CMB is like a cosmic recipe book. It lists the quantities of the fundamental components, and with that information, cosmologists can project forward to see how the dish, the universe, will turn out billions or even trillions of years later. What the CMB tells us is both fascinating and sobering. It confirms that ordinary matter makes up less than 5% of the universe. Dark matter contributes about 25%, and dark energy dominates with about 70%. Each of these components plays a role in shaping the future. Ordinary matter gives us the visible stars, planets, and life. Dark matter acts as the gravitational scaffold, holding galaxies and clusters together. Dark energy, however, drives the expansion of space itself, pushing galaxies apart at an accelerating rate. Together, these forces sketch out a destiny that is far stranger than the simple models early scientists once imagined. The most profound implication of this blueprint is the fate of cosmic expansion. Before the CMB was studied in detail, many scientists assumed the universe's expansion would eventually slow, perhaps halting altogether. Gravity, they believed, might be strong enough to pull everything back together in a cataclysmic big crunch, but the CMB, combined with other observations, painted a very different picture. Instead of decelerating, the universe's expansion is speeding up. Galaxies are racing away from one another faster and faster, as if propelled by an unseen force. The CMB provided critical evidence for this acceleration, showing that dark energy is not a temporary phenomenon, but a dominant feature of the cosmos. If dark energy continues as it has, the long-term future becomes clear. The universe will expand forever, growing colder, darker, and more isolated with time. Galaxies that are visible today will eventually slip beyond the cosmic horizon, receding so far and so fast that their light can never reach us. The night sky, once rich with billions of galaxies, will slowly empty. In the very distant future, any observers in what remains of the Milky Way's descendants might look out and see only their local galactic group, with no evidence of the wider universe. They would live in a cosmos that feels small and lonely, unaware that it was once vast and interconnected. The CMB tells us this not as speculation but as projection, a consequence of the physics encoded in that ancient light. And yet, the blueprint of the future is not only about vast, bleak timescales, it is also about the immediate cosmic evolution we are still witnessing. Those tiny fluctuations in the CMB, once minuscule differences in density, became the seeds of galaxies. By comparing what the CMB tells us about those seeds with what we see in the present, cosmologists can predict the continued growth of structures. Clusters of galaxies will merge, superclusters will stretch across cosmic web filaments, and the universe's large-scale structure will become even more pronounced in the near future of billions of years. The ripples frozen into that ancient light continue to shape the universe's growth, guiding matter as it falls into invisible wells of dark matter. This also raises another point. The blueprint is not deterministic in a rigid sense, but probabilistic. The CMB does not dictate a single unalterable future. Instead, it provides the initial conditions, the probabilities, the framework within which cosmic evolution unfolds. It shows us what was possible, what was likely, and what paths the universe could take. In this sense, the universe's oldest light functions like a set of architectural plans. It provides the design, but the details are filled in as time passes. Galaxies could merge in one way or another, stars could form in different places, but the overall structure remains consistent with the blueprint. What makes the CMB especially powerful in predicting the future is its precision. Instruments such as COBE, WMAP, and Planck have measured the fluctuations in the oldest light with exquisite accuracy, down to microkelvin variations. From these patterns, scientists have been able to determine the age of the universe to within a fraction of a percent, the curvature of space, and the exact proportions of cosmic ingredients. With this level of detail, the predictions about the universe's long-term behavior are not vague guesses but carefully calculated outcomes. The fact that we can look at a faint glow across the sky and extract predictions billions of years into the future is one of the greatest triumphs of human curiosity. The blueprint of the future also extends to the fate of stars and planets. Based on the CMB revelation of cosmic composition, we know how much fuel the universe has for star formation. Already, star formation rates have peaked and are declining. In the far future, the remaining gas will be used up and fewer new stars will be born. Over trillions of years, the cosmos will gradually transition from one filled with bright, youthful stars to one dominated by long-lived red dwarfs, faint and enduring. Eventually, even those stars will burn out, leaving behind remnants, white dwarfs, neutron stars, black holes. The blueprint does not show us every detail, but it sets the trajectory toward a universe where light itself becomes rare. Another surprising aspect of this cosmic blueprint is what it suggests about ultimate endings. If dark energy continues to behave as it does today, the universe may face what is sometimes called the heat death or big freeze. Expansion will continue endlessly, temperatures will asymptotically approach absolute zero, and usable energy will become scarce. Entropy will dominate, and the cosmos will fade into darkness. However, if dark energy is not constant, if it evolves with time, other possibilities arise. Some theories suggest it could grow stronger, tearing apart galaxies, stars, planets, even atoms in a scenario known as the Big Rip. Others propose it could weaken, perhaps allowing gravity to regain dominance, leading to a collapse. While we do not yet know which path is certain, the CMB gave us the critical starting point for exploring these possibilities. Without it, we would not even know which futures to consider. Beyond physical predictions, the blueprint hidden in the universe's oldest light has philosophical implications. It challenges us to think about time in a way that stretches beyond human lifespans, beyond civilizations, beyond even the existence of stars. To know that the future is encoded in the faint glow of ancient photons is humbling. It reminds us that we are temporary participants in a story that spans trillions of years, and yet the fact that we can read that story at all is extraordinary. Our ability to build instruments, to analyze patterns, to decode the universe's blueprint shows that even though we are small, we are capable of comprehending the vast. This perspective also gives us a sense of responsibility. If the universe's oldest light reveals the blueprint of the future, then our choices matter within that framework. While we cannot alter cosmic expansion or change the nature of dark energy, we can shape the future of our species, our planet, and perhaps even our role in the cosmos. The CMB tells us what kind of universe we live in, but it does not dictate how we choose to live within it. It sets the stage, but we decide how to act upon it. In the realm of science, the blueprint continues to drive innovation. Each revelation from the CMB inspires new theories, new instruments, new missions. We continue to refine our measurements, to test whether dark energy is truly constant, to search for signatures of inflation, to look for anomalies that might hint at new physics. In doing so, we expand the blueprint, adding detail, correcting errors, and pushing the boundaries of knowledge. The CMB may be ancient, but its relevance is always new, always pointing us toward the next horizon. Perhaps the most poetic way to understand this is to see the CMB as a bridge between what was and what will be. It is the light of the past, yet it shines on the path ahead. In its patterns, we see not only the seeds of galaxies, but also the destiny of the cosmos. It reminds us that the universe is not random chaos, but a structured, evolving system, one whose future is written in the language of physics. And though the end may be cold, dark, and distant, the journey itself is filled with wonder, beauty, and meaning. So, when we say the universe's oldest light reveals the blueprint of the future, we mean that it gives us more than just a glimpse of what was. It shows us the architecture of everything, the scaffold of time, the probabilities that define existence. It is a reminder that the cosmos has a story, one that is not only vast in scale, but also deeply interconnected. Every photon from the CMB carries part of that story, whispering not just about the dawn of time, but about the far horizon of eternity. In the end, the greatest revelation is not that we know the universe will expand forever, or that stars will burn out, or that galaxies will drift apart. The greatest revelation is that within a faint, nearly invisible glow in the sky lies the knowledge of past, present, and future all at once. The universe's oldest light is the script of creation, the architecture of structure, and the prophecy of destiny. To study it is to peer into a cosmic mirror, one that reflects not just where we came from but where we are going, reminding us that our brief moment under the stars is part of a grand design billions of years in the making. When we talk about the universe's oldest light, the cosmic microwave background, we are often swept away by the immensity of its scientific meaning. It is a window into the beginning, a record of conditions from nearly 14 billion years ago, a map of the cosmos that explains how stars and galaxies emerged. It is numbers, equations, and models, wrapped in the faintest glow stretched across the sky. But beyond the science lies something deeper, something profoundly human. The story of the universe's oldest light is also a story about us, our curiosity, our smallness, our resilience, and our desire to understand where we belong in the vast expanse of creation. When human beings first gazed up at the night sky thousands of years ago, they saw mystery and beauty. They saw pinpricks of light scattered across darkness, and they wove myths and legends to explain them. The sky became a canvas for gods, for destinies, for the questions of life and death. Back then, we had no way of knowing that beyond the stars visible to the naked eye lay an entire universe filled with galaxies, stretching out for billions of light years. We had no inkling that the faint afterglow of creation itself was bathing us in light older than time as we know it. And yet, even in those early days, the human impulse was to seek, to question, to find meaning in the vastness. Fast forward to today, and that impulse has not changed. What has changed are our tools and our knowledge. With radio telescopes, satellites, and mathematical theories, we have pulled back the veil, revealing the faint echo of the Big Bang. That light is not just a scientific curiosity, it is a connection to the beginning of everything, to realize that the photons reaching our detectors today have been traveling since the universe was only a few 100,000 years old, is humbling beyond measure. It places us in a timeline so immense that human history becomes the briefest flicker. Empires, wars, civilizations, even the rise and fall of species, all of it has unfolded in a fraction of cosmic time, while this light has been on its uninterrupted journey to us. This perspective can make us feel small, almost insignificant. What are we, after all, in a universe where most of the matter is invisible, where the scale is measured not in miles or even light years, but in billions of light years? What is a single human life compared to the sweep of 14 billion years? These questions strike at the heart of human perspective, and they are not new. Philosophers, poets, and scientists have wrestled with them for centuries. But the discovery of the cosmic microwave background gives those questions a sharper edge. We are not just tiny, we are fleeting, and the universe is far stranger and more expansive than we once believed. And yet there is another side to this. To say that we are small is true, but to stop there misses the deeper truth. The fact that we can even detect the universe's oldest light is extraordinary. Out of all the known phenomena in the cosmos, life, and especially conscious, reflective life, is rare. We are beings capable of building instruments sensitive enough to detect fluctuations in temperature of a few millionths of a degree across the entire sky. We are capable of interpreting those signals, translating them into a story of cosmic origins. In other words, though we are small in size, we are vast in mind. We have within us the capacity to stretch across time, to imagine the birth of galaxies, to contemplate the end of everything. That is no small feat. The human perspective, then, is one of paradox. We are insignificant in the scale of the universe, yet significant in our ability to comprehend it. Photons of the cosmic microwave background traveled for almost 14 billion years through empty space, and it is only here, on a small rocky planet orbiting an average star in the corner of an average galaxy, that they found creatures capable of listening. In a sense, we give that light meaning. Without consciousness to interpret it, the CMB would simply be radiation filling space, unnoticed and unremarked. But with us, it becomes history, narrative, knowledge, even inspiration. This realization changes how we see ourselves. It shifts the human story from one of mere survival to one of participation in something cosmic. Every scientific breakthrough is not just a discovery about the universe, but also a discovery about who we are and what we can do. When we map the CMB, we are mapping not only ancient photons, but also the human spirit's refusal to remain ignorant. We are declaring that curiosity is as much a part of us as breath and blood. That, too, is part of the human perspective, the recognition that to seek the universe's secrets is, in a way, to seek ourselves. The CMB also teaches us humility in a profound way. For centuries, humans believed themselves to be at the center of creation, the earth at the center of the cosmos, humanity at the pinnacle of existence. One by one, science stripped away those illusions. We are not at the center, we are orbiting a star on the edge of a galaxy among trillions. We are not made of the dominant substance in the universe, we are built from a minority ingredient, while dark matter and dark energy rule unseen. The CMB confirms this humbling truth. It shows us that our place is not central, not privileged, but part of a vast tapestry, and yet this humility is not defeat. It is freedom, the freedom to see ourselves honestly, to understand that meaning does not come from being the center, but from being a conscious thread in the larger story. The human perspective also brings with it questions of time. The CMB tells us that the universe had a beginning, that it has evolved, and that it will continue to evolve long after we are gone. To know that the cosmos has a timeline billions of years long forces us to reconsider our own. Human lives, short as they are, take on new dimensions in this context. On one hand, we seem smaller than ever. On the other, we become infinitely precious because our time is brief. If the CMB shows us eternity, it also shows us the urgency of the moment. We are here only for a blink in cosmic terms, and that makes every blink meaningful. This sense of perspective can also shape how we treat one another and our planet. If we are all passengers on the same tiny world, adrift in a universe vast beyond comprehension, then the divisions we create among ourselves, borders, races, ideologies, begin to look shallow and temporary. The CMB does not distinguish between one human and another. Its light falls on us all equally. It is the most democratic of truths. We are all children of the same beginning, shaped by the same cosmic history. To embrace this perspective is to recognize our shared belonging, not just to Earth, but to the universe itself. Moreover, the human perspective is not just about awe and humility, it is also about responsibility. We are the only known species capable of understanding the universe's blueprint, of holding the knowledge of beginnings and endings in our minds. That gives us a responsibility to preserve that knowledge, to pass it on, to use it wisely. The CMB reminds us that the universe will go on with or without us, but our place within it is not guaranteed. If we wish to continue participating in the cosmic story, we must safeguard our planet, nurture our civilization, and ensure that our curiosity endures. For some, the revelations of the CMB may spark existential dread, the sense that nothing matters in the face of such vastness, but the human perspective can turn that dread into wonder. Meaning does not have to be written into the fabric of the universe for it to exist. Meaning is what we create, what we choose to value. The fact that we are small does not make us meaningless, it makes our choices even more important. The fact that we are fleeting does not make us irrelevant, it makes our brief existence all the more precious. The universe's oldest light is not telling us to despair. It is inviting us to marvel, to reflect, and to rise to the challenge of being conscious in a cosmos that is mostly unconscious. Even in art, literature, and philosophy, the CMB has resonance. It is the ultimate metaphor for memory, the universe remembering its own childhood and sharing it with us. It is the ultimate metaphor for connection. Photons that began their journey before there were stars, now entering our instruments and our minds. It is the ultimate metaphor for perseverance, a signal that has survived billions of years of cosmic change to reach us intact. Artists and poets may not speak in terms of microkelvin fluctuations, but they understand the beauty of a universe that whispers across time. Scientists may measure data, but in their awe lies the same wonder that inspired ancient stargazers. The human perspective bridges these two, data and wonder, knowledge and meaning. There is also something profoundly intimate about the CMB. Though it is cosmic in scale, it touches us individually. Every human who has ever lived has been bathed in its glow, whether they knew it or not. Every breath you take, every step you walk, every night you sleep under the stars, you are living within that ancient light. It is not out there in some distant corner of the universe. It is here now, surrounding you, entering your body, passing through your skin. The universe's oldest light is not just a relic we observe. It is part of our environment, part of our daily existence. That too changes perspective. The cosmos is not remote. It is immediate. It is not cold and alien. It is woven into the fabric of our lives. In the end, the human perspective on the CMB is a lesson in balance. It balances smallness with greatness, humility with significance, science with meaning. It shows us that we do not need to be the center of the universe to matter. We matter because we are aware, because we can reflect, because we can choose. We matter because we can take the faint whispers of ancient photons and turn them into stories, into understanding, into wisdom. So, as we continue to study the universe's oldest light, let us not only see it as a scientific treasure, but also as a human one. It is a reminder that knowledge is a gift, that curiosity is our inheritance, and that perspective is our greatest tool. It teaches us to stand in awe, to look beyond ourselves, and yet also to cherish the fragile beauty of our brief lives. The CMB may reveal the surprising origins of the cosmos, but in doing so, it also reveals the surprising potential of humanity, the potential to see, to know, and to find meaning in the vast silence of space.